Hello, welcome to Electronics Education. I'm Vincent Chang. Today we are going to continue our study on the small signal model for the MOSFET. Small signal model. MOSFET small signal model part 1. High pre-pi model versus T model. High pre-pi model versus T model. Let's quickly review what we learned before regarding the MOSFET transconductance. You have the DC operating point and you send in the AC input voltage. Then you're creating an output AC current, right? Up, down, up, down. So the purple triangle highlight the relationship among the output AC current and the AC input voltage and the AC performance parameter when it comes to the small signal transconductance. ID equals GM times the VGS. Now here comes the first one, so-called hybrid pi model. The hybrid pi model. So we simply take the result from the previous slide. This is the result, right? ID equals the GM times VGS. We simply take this, keep this, and just draw it out. So now drain, source, and gate. Gate, source, a drain. So assuming the fourth terminal body is connected to the source. So this current, the drain current, the current is called ID, right? So ID equals GM VGS. So what is VGS? VGS is the boss, because boss control the current. The boss. The boss is here. Boss, look at your left-hand side. Boss is the VGS. So it's the voltage control current source. It's the voltage control current source. It's the input voltage control the output current. So voltage control current source. So it's the dependent source. Dependent source. So we'll use circle represent the independent source. And we use a diamond shape to represent the dependent source. So voltage control current source. So now here's the starting point. Tells us the first model called MOSFET high pre-pi model. So now I'm starting from this and take you to the second model, which is the T equivalent circuit model. The T equivalent circuit model. By the way, why is called hybrid pi model? Why is called pi? You can just simply put some. Imagine there's something connected between gate and the source. So it kind of resemble the mathematical symbol 3.14, which is pi. Okay, so it's called hybrid pi model. So now I'm taking you from the hybrid pi model, we're moving into another model called T model. So watch carefully. T, it looks like a T. See a T? T shape. On the top is the pi shape. On the bottom is the T shape. And I'm taking you step by step because it's the floating gate, no gate current. So source current has to be the same as the drain current. Gate, source, drain. Floating gate, oxide. So drain current has to equal to the source current. So look at the first, the equal sign. IS equals ID. Any problem? IS equals ID. Why? Because there's no gate current. Gate current is 0. And then IS equals IS. So see, look at the model. Look at the model. Pay attention to the model. ID now equal to IS. So you see the IS is the current control current source. On the top is the voltage control current source. But on the bottom is the current control current source. The ID bus is IS. And the controlling ratio is unity, is 1. Current control, current source. And now here comes the third equal sign. We simply change the conductance into the resistance. Okay? So what's the value for the resistance? 1 over Gm, 1 over the conductance part. So now, I want you to just take out, you can just use a piece of paper to cover out the ID, the one in the middle. Just focus on the beginning and the end. The beginning tells you the IS. The end tells you VGS over 1 over Gm. So it's simply a relationship from the most simple circuit theory around the world, which is called Ohm's law, right? So based on this, let me ask you, what's the value, a proper value for that question mark, for that resistor? What's the proper value for that, the good, right description for that resistor when the question mark is located? 1 over Gm. Right? Why? 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 Ohm's law. Ohm's law. I wanted you to focus on the beginning and the end, right? The beginning tells you the current, IS. The end tells you VGS divided by that resistance. So what is that resistance? 1 over Gm. 1 over Gm. This is the T model. This is the T model. On the top is the hybrid pi, on the bottom. So one equation can take you from the hybrid pi model to the T equivalent circuit model. Here's the takeaway. This one is the T model. On the top is the hybrid pi model. You know how to take from the hybrid pi model to the T model. So what's the key message here? Both models are equivalent to each other. Use any of the model to solve any circuit should have the same outcome. You just have the two equivalent pathway. Two equivalent pathway. But one way, but I mean the equivalent means the destination. But the journey, one could be very smooth. The other one could be very bumpy. Okay? Let me ask you. Here's the key message. What's the resistance looking from the gate? What's the resistance between gate and the source? Looking into the gate. It should be infinite, right? The answer is infinite. Open circuit, no current. There's no current. Look at your left-hand side, no current. IG, take note, because IG is 0. IG is 0. So the resistance between gate and the source looking into gate is infinite. Let me ask you, what's the resistance between gate and the source? Yet looking into source. What's the resistance between gate and the source looking into source? The answer is 1 over GM. You get it? This is the key message. Before you move on to the next lecture, make sure you remember this. It's very, very important. If I'm asking you, what is the resistance between gate and the source, then I expect you to ask me back, sir, which terminal I'm supposed to look into? If looking into gate is infinite, if looking into source is 1 over GM. Why there's a difference? Because it's not a 2-terminal device. It's the 3-terminal device. Okay, this is the key. This is also the key message, key takeaway out of this lecture. I hope you receive something, especially this very important one, from this lecture. Thanks for watching.